Paper bag or plastic bag? Which one is better for the environment? Most people answer instantly, and most people are answering the wrong question. Welcome to Life Cycle Assessment from scratch. No black boxes. By the end of this episode, you will know exactly what an LCA is, the 4 steps every study must follow, and the ISO rules that keep it honest. Intuition says paper. It is natural, it degrades, it comes from trees. Plastic is the villain. Case closed, right? But a paper bag does not appear from nowhere. Trees are harvested. Pulping consumes enormous amounts of water and energy. And paper is heavy, so shipping it burns more fuel. The plastic bag starts from fossil feedstock, which sounds bad, but manufacturing it takes surprisingly little energy. Its real problem shows up at the end of its life. So which bag wins? It depends on where you look. Judge only the factory, plastic wins. Judge only the landfill, paper wins. The honest answer needs the whole story from cradle to grave. That is exactly what life cycle assessment does. Life cycle assessment is a standardized method for quantifying the environmental impacts of a product or service across its entire life, from raw material extraction to final disposal. Every product moves through the same chain. Raw materials are extracted. They are manufactured into a product. The product is distributed, then used, and finally disposed of or recycled. The first stage is the cradle. The last is the grave. A full study that covers everything in between is called cradle to grave. But not every study needs the whole chain. A cradle-to-gate study stops at the factory gate. It is common for materials like 1 kilogram of steel or cement, where the final use is unknown. Cradle to grave covers the full chain. And if end-of-life materials loop back as new raw materials, we call it cradle to cradle. The boundary you choose changes the answer you get, so it must always be stated explicitly. Keep this picture in mind. Every SEMA Pro model we build later in this series is just this diagram, filled with real numbers. LCA is not a vibe. It is governed by 2 international standards. ISO 14040 gives the principles and framework. ISO 14044 gives the detailed requirements and guidelines. The framework has 4 phases: goal and scope definition, inventory analysis, impact assessment, and interpretation, which is drawn tall for a reason. It talks to every other phase. Notice every arrow points both ways. LCA is iterative. Your impact results might reveal that your system boundary was too narrow, sending you back to goal and scope. That back and forth is not a failure. The standard expects it. And the standard has teeth. You must define a functional unit. You must state your system boundary and cut-off criteria. And if you publish a comparison between products, a critical review by an independent panel is mandatory. We will unpack each of these, starting with goal and scope, right after this. Phase 1, goal and scope. This is where most LCA studies are quietly won or lost before a single number is collected. 3 decisions live here. First, the functional unit. It is the most misunderstood idea in LCA. The rule: define the function the product delivers, never the product itself. Suppose we compare biogas and LPG for cooking. 1 kilogram of fuel sounds fair, but it is meaningless. The 2 fuels have different energy contents and different stove efficiencies. A kilogram of each does not cook the same amount of food. The honest basis is the function. 1 megajoule of cooking energy actually delivered to the pot. Stove efficiency is now inside the comparison where it belongs. Every input and every emission in the study will be scaled to this unit. Second decision, the system boundary. Draw a line around the processes you will model: fuel production, transport, combustion. Inside the line, you are responsible for every flow. Everything outside must be declared. Are we ignoring the manufacturing of the stove itself? Perhaps if both options use similar stoves, it cancels out. but ISO 14044 demands you state the exclusion and justify it. Silent omissions are how studies get rigged. Third, cutoff criteria. You cannot model every screw and every gasket, so you declare a rule up front. For example, flows below 1% of mass or energy may be dropped, as long as the total drop stays under 5%. The rule is chosen before the data, so it cannot be abused after. Phase 2, inventory analysis. This is the accounting phase, and usually 80% of the work. The goal, a complete ledger of everything crossing your system boundary. The atom of every inventory is the unit process. Inputs enter on the left: cattle dung, water, a little electricity for stirring. The product leaves on the right: biogas. And then there are the flows nobody invoices: emissions straight to nature. Methane leaking from the digester goes to air, not to another process. These are called elementary flows, and they're the raw material of Phase 3. Chain unit processes together, and the flowchart from scene 2 reappears, now with numbers attached. Where do the numbers come from? Your own measurements when you can get them. A background database like EcoInvent for everything upstream. Literature values as the fallback, always with the source recorded. One trap before we move on. The digester does not make only biogas. The leftover slurry is a valuable fertilizer. 2 products, 1 process. So who owns the methane leakage? The gas or the fertilizer? That is the allocation problem, and ISO has a whole hierarchy for it. We will face it head-on in the SEMA Pro episodes. Phase 3, impact assessment. The inventory gave us a long list of substances. Impact assessment turns that list into meaning. 3 steps. Classification sorts each substance into the impact categories it affects. Characterization converts each one into a common unit within its category. Normalization and weighting can compress further, but under ISO they are optional, and for public comparisons weighting is not allowed. Here is characterization with real numbers. Say our inventory per functional unit contains 1 kilogram of carbon dioxide, 50 grams of methane, and 1 gram of nitrous oxide. Methane is a far stronger greenhouse gas. Over 100 years, 1 kilogram of fossil methane traps as much heat as about 29.8 kilograms of CO2, using the latest IPCC factors. So 50 grams of methane becomes 1.49 kilograms of CO2 equivalent. Nitrous oxide is more extreme still at 273. Add them up, 2.76 kilograms of CO2 equivalent. Notice the methane, tiny by mass, outweighs the CO2 itself. This is why LCA refuses to judge by mass alone. One vocabulary item you will meet in every method list in SEMA Pro: midpoint versus endpoint. Midpoint indicators stop partway along the cause-effect chain, like kilograms of CO2 equivalent. Endpoint indicators push all the way to damage on human health or ecosystems. Endpoints are easier to communicate. Midpoints are more certain. Methods like recipe give you both. Phase 4, interpretation. Not a summary at the end, but the phase that talks to all the others. Remember the tall box in the ISO diagram. 3 tools do most of the work here. First, contribution analysis. Break the total impact down by life cycle stage. Suppose fuel production carries 62% of the climate impact, combustion 28, transport a mere 10. Now you know where improvement effort pays off and where it is wasted. Second, sensitivity. Take your shakiest number, say the methane leakage rate, and push it across its plausible range. If the ranking of options survives, your conclusion is robust. If it flips, honesty requires you to say so, and that single parameter becomes the headline of the study. Third, the formal ISO checks. Completeness. Is every relevant flow in? Sensitivity. Were the shaky numbers tested? Consistency. Were methods and data applied the same way to every option compared? pass all three, and only then are you allowed to write conclusions and recommendations. In the next scene, we run the whole four-phase framework on a real Kathmandu Valley problem. Let's run the whole framework once on a real question. A Kathmandu Valley household cooks dinner. Should it use biogas from a backyard digester or bottled LPG? All four ISO phases quickly. Phase 1. Functional unit. 1 megajoule delivered to the pot, so stove efficiency is baked in. Boundary, cradle to grave. 2 options compared on identical terms. Phases 2 and 3, side by side. For biogas, the digester runs almost twice per functional unit, and here is the number that matters. Nearly 1 gram of methane leaks per megajoule. Characterize the inventory, and biogas lands at 0.159 kilograms of CO2 equivalent. LPG burns more fossil carbon at the flame, but its supply chain leaks far less methane. It lands at 0.119, lower than biogas. Phase 4, interpretation. On these numbers, LPG wins by about 25%. And that is the counterintuitive lesson from the very start of this episode. The greener sounding option lost. But look closer. The entire verdict rests on one shaky number, the digester leakage. Seal the digester properly, and biogas wins outright. So the honest conclusion is not just LPG wins. It is biogas is better only if leakage is controlled. That sentence is worth more than the ranking. So, in one episode, LCA judges a product's whole life. ISO gives 4 iterative phases. The functional unit keeps comparisons honest. Impact assessment turns a list of emissions into meaning. An interpretation, with sensitivity, tells you how much to trust the answer. From here, we stop drawing and start building. Next, we open SEMA Pro and model this exact system with real data. Then, for the no black box crowd, we write the LCA engine ourselves in Python, 3 lines of matrix algebra, and we finish with a full Kathmandu case study, start to finish. If you want the whole series, subscribe so you do not miss the SEMA Pro builds. And drop a comment. What fuel does your region cook with? It might become the next comparison. See you in the software.